Hello everyone, welcome to Dakshana e-classroom program. So in today's lecture, we are going to start a new topic, and that is elasticity and viscosity. Elasticity and viscosity are basically two properties. Elasticity is a property related to solid, and viscosity is a property related to liquid. So broadly, mainly we will focus on this topic, but in this chapter actually it's more about understanding the behavior and some properties, mechanical properties of solids and liquids. So first, solid, everyone is familiar. Solid, like here atoms are arranged, is it? So like all material, whatever it is, they are made of some atoms and molecules. So solid we can define simply, it's a material. Solids are a material in which which has fixed definite shape and volume. That a material which is having definite or fixed shape and volume can be categorized as solid. So solids are made of like what? Atoms and molecules. When we look at it, when we study in detail actually, then it is observed that some solids have the arrangement of atoms in a regular, proper, fixed manner, and some solids have like random arrangement of atom. So based on that, we categorize solids in two categories. So solids been categorized into two categories. So, or I will say there are two types of solid. Are two types of solid. One is crystalline solid and amorphous solids. So what is crystalline and what is amorphous? In crystalline solids, the atoms and molecules are arranged in a proper or regular three-dimensional pattern. So in crystalline solids, atoms or molecules are arranged in a regular three-dimensional pattern. So a solid which is having a proper arrangement of atoms or proper regular arrangement of atoms in three dimensions, we will call that as a crystalline solid. And amorphous, like when atoms are arranged, atoms or molecules basically, you can write either arranged in random or no order, is it? Or no regular arrangement. Of atoms and molecules. In crystalline solid, because like here atoms and molecules are arranged in a proper regular three-dimensional pattern, so there is a fixed repeating, fixed unit actually. We can try just identify, we can remove one unit, and if we repeatedly pack those units, then like in large number of units we are packing, then we get crystal or crystal lattice. So these are few just terms related to solid. We are not going to talk about more in these much detail about these points. You will study about these things in chemistry in the chapter that is called solid state. Our focus in this chapter is something else, that is more about understanding like some mechanical properties of solid. So okay, we understood that in crystalline solids the arrangement of atoms and molecule is in regular manner. In amorphous, it's in random manner. But when we look at actually molecule level or atomic level, is it, so then solids, how exactly they are bonded, is it? So like depending on some materials have like covalent bond, ionic bond, and different types of bonds are there. But in general term, if we look at it actually, so in solid, let's say this is one molecule and there is another molecule and they have some separation actually. R is the distance between. And if we look at it actually, like because they have some charge, nucleus is there, electron cloud outside there. Similarly, another atom has nucleus positively charged and electron cloud. So what is there, like they are electrically charged, I mean like electron cloud and nucleus. Overall, if I look at one atom, it's electrically neutral, but there is charge. So they are interacting basically. It means atoms interact. That's why like for this pair of system, its potential energy can be defined. So the potential energy for this system is defined some A r raised to power 6 minus B r raised to power 12. This is one form of like potential energy function for a pair of molecule, a pair of atom in solid. So what is happening, like these atoms are like bonded together with some force, is it? So we can even like, what is that force? We know actually it's minus du by dr. If I differentiate it, then that will be like minus, this is a r raised to power 6 differentiation of this d by dr minus b r raised to power minus 12. And if I differentiate it, then I will get minus 6 a r raised to power minus 7 plus 12 b r raised to power minus 13. This is the depending, that is how like force between two molecules actually depends. And if we plot its potential energy function versus separation graph, we will get more detail about it, what exactly happening here. That graph U versus R looks like this. So here there is a particular like proper separation R naught, at which what will happen, U potential energy is minimum. And when potential energy is minimum, what does it mean? That means the system will be in stable equilibrium at that point. So here system will be in stable equilibrium. So means if we are simply leaving the solid lattice, then atoms will be staying at a separation where they are in stable equilibrium. Means the potential energy of interaction between two atoms is minimum. The potential energy function is given by this. We can even calculate this R naught. So we know actually at this point the slope of du by dr, that actually is equal to force, will be equal to 0. So we can calculate this is the basically at this point you can write this is a stable equilibrium separation between two atoms or molecules. Okay, so at this point I can write system in equilibrium or pair of atoms basically in equilibrium. And equilibrium means force between them will be 0. So I got already force relation minus 6 a r raised to power minus 7 plus 12 b r raised to power minus 13 equal to 0. Then I will get exactly that r separation. So this will be like I can take 6 r raised to power 7 minus out, and let me write minus also. Then it is a. Here it's we are left with only a, and here it will be minus 2 b and r raised to power minus 6 equal to 0. So that means one, either this quantity is equal to 0 or this quantity is equal to 0. This is 0 only when r is equal to infinity. So means this implies either r raised to power minus 7 equal to 0 or a minus 2b r raised to power minus 6 equal to 0. So this is equal to 0 when r is equal to infinity. That doesn't make much sense because we are not at r is equal to infinity. Yes, it will be 0, but we are not interested. That's not like useful for us. Here from this point we can get a. So this is basically a minus 2b by r raised to power 6, and this implies r raised to power 6 is equal to 2b by a, and r is equal to this. So at this separation I will write it R naught. This pair of atoms will be in stable equilibrium. Is it? Potential energy of interaction of these two atoms will be minimum, and that's why the atom will be in equilibrium. Means if I simply allow, I am leaving the atoms, then they will be staying at some distance, right? The separation between these two atoms will be equal to this at equilibrium. So they will like be staying at this much separation because the system is having lowest and minimum in I will say interaction potential energy. Now okay, that is one thing. Now what happen actually, like when we are using solids, is it for different purposes, maybe for construction material, maybe like we are making some is it some object which are useful, then they are going through some either stress, some force, some tension, something like that. So what happen actually, ultimately those all things get transferred to the atoms, is it? So because of that, like what will happen actually here, force, if it is like they are being pulled apart, then what will happen, the system will be shifting towards this side. Similarly, if they are being compressed, then the system or pair of atom will be shifting this side. They will not be, means pair of atoms will not be staying in equilibrium anymore. Okay, so now we will try to understand what happened in that case. We understood at this is the potential energy function. If we are simply leaving these two atoms, then they will be staying at a separation given by this, and this is your equilibrium separation, right? And another thing actually here, in this region, what is happening, like when potential energy is negative for that system, like we can say it's more of like stable equilibrium, the force between two atoms will be like attractive. For potential energy positive, the force become actually repulsive, because that you can correlate from your electrostatic chapter. So potential energy positive means what, k q by r, and that is positive only when both type of charges are positive or both charges are positive. And if they are of same charge, or like I will say positive or either both are negative, so when the nature of two charged particle is same, then definitely they will repel. When potential energy is negative, when one of the two charges are of opposite nature, so then always they will attract, is it? So that is one thing. And now in this situation we understood it up to here. This is equilibrium position. So now we are trying to understand, like if we are pulling them, is it, what will happen to them actually? So now for this reason I will write, for this reason u is less than 0. This implies force between atoms will be attractive, is it? And for u greater than 0, we can write force is repulsive. Clear? Okay, but equilibrium position is this. So always, like if we are leaving the system, it will always try to come to this much separation. So now in this situation actually, this bond, if we look at it like more in detail, these are two atoms, and here this bond actually like it behave like a spring. How? Because at this much separation, if separation between these two is r0, then they will be in equilibrium. If you want to increase the separation, if you want to apply some force between these two atoms, what will happen? Actually the separation between atoms will increase, so that it will be shifting toward this side, and what it will want, it will try to again it will try to come to the equilibrium position, means lowest energy state. So in that situation, like it will be like acting like a spring, is it? So when we are pulling them, this spring is stretched. When you are releasing them, it will again come to back its position. But does it happen with all atoms? Does it happen exactly same thing with all type of material? No. There are different types of material. So based on that, we first define some property, and then we categorize the material. The thing is, there are some material which when we are like applying some force, we call this force as deforming force. So deforming force basically try to change the shape or try to deform the atoms or the solid. So deforming force it is external applied force which try to change shape of solid. We call that as deforming force, right? Another thing is that, so this is deforming force. Beside that, between any two atoms or molecule, there will be another this force working, is it? What it is trying, it is exactly trying opposite of this. This force is trying to pull them apart, and this spring force will be trying to bring them closer again, is it? So this try to restore its shape. This force, that is the internal force, that is the force because of like bonding, and this force try to restore the original shape, and we call that as restoring force. So another is restoring force. It's internal force, it is force between atoms and molecules or molecule which try to restore the shape of solids, is it? When external deforming force is removed, it will be acting always, but it will try to, because until like when external deforming force is applied, then how it can restore? It's not possible. But when we are removing this deforming force, it will try to restore back to its original shape, right? That is termed as deforming force. Now depending on actually like what is exactly type of solids, different types or different materials have different behavior. When this deforming force is applied, some material, some solids have the capacity, have the property that if you are applying deforming force, material solid will get deformed. As soon as you remove the deforming force, it will again regain its original shape and size. This type of material we call as elastic material, if it is regaining its original shape and size, and this property of solid is termed as elasticity. Similarly, there are another type of material where like if you are trying to, let's suppose, pulling them, is it? We are trying to deform, and once like you deformed by applying external deforming force, and let's remove the deforming force. now in this case there is second, like this type of material which does not regain its original shape and size. As like whatever the shape it is deformed, it will simply stay in that shape. Is it? These type of material we call plastic materials, right, or non-elastic material. So we will like focus more on it, like we will try to understand some like we will define some mechanical terms, we will try to understand their meaning, like that is stress, strain and different ways, so that we can understand more about the properties of solids. So this is just about deforming force, restoring force, exactly what is happening inside solid at molecular or atomic level. Inside the solid, each, or like you can say pair of molecules, pair of atoms, they are bonded together by one bond, or that we can, this bond we can understand it's equivalent to one spring, is it? So if we are not doing, we are not disturbing the solid, then by itself solid molecules or atom have tendency to stay there at some particular separation, and that separation is termed as your equilibrium separation, and that depends on its potential energy function. So wherever like this separation will be the point, or the you can say the distance between two atoms where the potential energy is minimum, they will try to stay at this point. But when we apply some external force, then we are disturbing this separation. It molecules are trying to stay there, but we will try to either bring them this here or there. That is what happened when we apply some external deforming force. So now after applying deforming force, different material are behaving in different manner. Let's understand their properties and how and which type of material is behaving in which manner. So here two things are there, one is deforming force, another is restoring force. Deforming force trying to change or trying to deform the solid body. Restoring force, it's internal force in between the molecules, it get developed when we are disturbing the equilibrium separation between two molecules or atoms. Then how exactly, after like removing deforming force, how exactly a solid is behaving? Based on its behavior, we are categorizing the solid broadly into two categories. One is called perfectly elastic solid or material, another is called plastic material. So what is exactly perfectly elastic material? Perfectly elastic material, we can say a material which on removing the external deforming force has tendency to regain its original shape and size perfectly. That material is termed as perfectly elastic material, and this property of solid, by virtue of which it regain its original shape and size on removing external deforming force, that property is termed as elasticity. So let me write both of these terms. So perfectly elastic material, a material or solid which regain its original shape and size on removal of external deforming force. So material or solid which exactly like which regain its original shape and size on removal of external deforming force is called as perfectly elastic material, right? Ideally, and if we look at it, actually there does not exist any ideal perfectly elastic material. Means there is no material which regain its shape and size perfectly, is it? So ideally this is just in concept. Perfectly elastic material, it's an ideal concept. No material is perfectly elastic. But yes, there are few material which have like we can say which almost regain its original shape and size, is it? So the best I can write elastic material. One of the example is quartz fiber. FIB. This is one of the example which has like you can say which approaches almost like perfectly elastic material, or we can call it it's almost perfectly elastic material. But ideally I already told there is no perfectly elastic material, and here I will define one more term that is called elasticity. So elasticity we can define it is a property of solids by virtue of which it is a properties regain its original shape and size on removal of external deforming force. So this property by which like a solid regain its original shape and size on removal of external deforming force, that property is termed as elasticity. Here sometimes some examples are asked, like if I give you, I will say there is one steel rod and another is rubber. You must be familiar. Rubber, let's say band is there. So what do you think, like which is more elastic, is it? So I'm giving you like steel rod, or I will write iron rod, you can take it. Another is rubber band, is it? What do you think, which is more elastic? Just think about it. I hope you might have got already your answer in your mind, that and you might be definitely like there are quite high chances that you must be thinking that rubber is actually more elastic. And the point is that the answer is not that, it's opposite. If I just compare the elasticity of steel rod and rubber band, then the answer is steel rod is having higher elasticity, or I can say steel rod is more elastic compared to rubber band. So whenever like some questions are asked similar, like two things or two three things are you're asked to be like asked to compare about their elasticity, then listen something like about it, then how we compare. So it's not more about like that you are expanding and it's stretching and then it's again regaining. It's more about the force actually. Higher the force you are applying and still it's able to regain its original shape and size, more will be the elasticity. So if rubber band is there, let's say this is a steel rod, and another it's let's say rubber band or rubber strap, you can write. Right. So here if you apply, let's say depending on how much thick or whatever it is there, if I apply here even like let's say 1000 Newton force, there is quite high possibility that it will still bear it, and it may stretch by small amount depending on how strong this is So it will depend exactly, but you can take like even 500 or 1,000 Newton force, but definitely it will bear. It may stress a little bit. If you remove, there is quite high probability that it will regain its original, or it will try to restore. Do you think real like this rubber band will be able to even bear this much load? It's definitely not. So it's not even in position to bear, it will simply break. Is it? It will not be able to bear that much load. So that's why like it's less elastic, it's more elastic. Means it can bear large load and still have the capability or probability of regaining its original shape and size. So it's more elastic compared to rubber band, strap or rubber band. So you can answer about this. So that is about elasticity or perfectly elastic material. It just definition. Yes, but there are some material which shows quite high elasticity, or their behavior is quite like large elastic, and there are some materials. So one of the example like which you can say it's like quite or best I will say elastic material, that is quartz fiber. Next is there are some type of material which if you are applying external force they will deform. Remove the external force, not at all, they will simply stay in that deformed shape, and that is termed as plastic material or perfectly plastic material. Okay, so perfectly plastic material can be defined as material solid which doesn't regain its original shape and size on removal of external deforming force, is simply termed as perfectly plastic material, plastic solid. Again, perfectly plastic material, it's also an ideal concept. If we look at it for like perfectly plastic material from the available solids or material we are having, then no, there is no one which exactly like which completely agree with this definition, but still we have like few material which like almost satisfy this condition perfectly, and we can write that best plastic material. So it's like wet clay, is it? You must be mitti, it's sort of like wet clay and paraffin wax. These are two examples which you can say they are almost like perfectly plastic material, because wet clay you can understand whatever the shape you are giving, just deform it, it will simply stay in that shape, it will not try to restore its original shape and size. So these are two examples which you can say almost approaches towards perfectly plastic definition of perfectly plastic material. So similarly we can define one property that is called plasticity. So it is the property of solid I will write by virtue of which solid does not regain original shape and size on removal of external force or external deforming force. So these are two definitions: perfectly elastic material, perfectly plastic material. Like this behavior, that why some material behave perfectly elastic and perfectly plastic, that depends on how exactly atoms and molecules are arranged in that lattice or crystal lattice or in that solid. So like by the definition that I told, two atoms in solid or like arranged such that they are staying at a particular separation where the potential energy between them is minimum, we define equilibrium separation. So at that time like it's staying there, but when we are applying some external deforming force, it's basically disturbing their equilibrium position, their lowest potential energy, and that result in some restoring force is developed between two atoms which try to regain its original shape and size, which try to bring both the atoms again back to minimum potential energy position. So because of that, some material have tendency to regain their original shape and size once external deforming force is removed. So this is about definition. Next things comes is like, okay, we are having solid, we are having material, we want applying some force. Now we want to see how exactly it will be deforming, and we will study some terms related to that deformation force. So for that we have stress, different types of stress. Now we will go more on mathematical terms. So we will study a few more terms that we can write, say mechanical properties of solid. We will try to understand that. So let's talk about next is stress. Now we are applying force or deforming force on the solid, and then we will see some terms about that. So that is, one is called stress. What is exactly stress? Stress, it's simply defined as deforming force per unit area. Is it? Stress. Another thing is in solids. So let's say this is a solid. We are applying some force. This is a deforming force. Its length is, let's say, L original. Area of cross section, I will write A. Is it? So now I'm here assuming that this force, it just it's not applied only at this point on this complete solid. It's applied at its complete surface. Is it? So we are pulling it by applying this force on its surface uniformly. We will assume it by itself. Is it? So means this force is completely applied on this complete whole surface. If it is like, let's say, cylindrical, then it's like this, like this. So this force is applied on its complete cross section. So stress in general term, I can refine, it's denoted by letter sigma. Is it? Stress is defined as, the definition, remember the definition comes, actually it's restoring force divided by area. That is termed as stress. Definitely unit, you can write, unit will be Newton meter square or Pascal. Correct? Now based on exactly like how we are applying the deforming force in exactly, because there is not only one way, there is no, like, not a single way to apply the force, there is not a single way to deform the body, there can be multiple ways. So based on that we we define different types of stresses. So one is, let's write, normal stress, or so normal stress here, like this is one of the example of normal stress. Here again, normal stress can be two types basically. This is also called longitudinal stress. Now first thing is, this above example is one of the example of longitudinal or normal stress. So if F force is applied normal to the area of cross section, is it? F force, you must be remembering here, its area of cross section is A. This is the force F applied. Then sigma, longitudinal or normal, this is divided. Again, the definition is restoring force divided by area of cross section. But when we look for some like practical cases, then always the magnitude of restoring force is equal to, or taken as equal to, external deforming force. So by definition it's equal to restoring force normal to cross section divided by area of cross section, or simply terms area. So that is, but this restoring force mathematically always become equal to external deforming force. So restoring force actually equal to deforming force, and that's why we can write stress is also equal to deforming force divided by area of cross section. But ideally the definition of stress is defined for restoring force, not for deforming force. But mathematically, because mathematically this is equal to that, that's why we can write stress is also equal to deforming force divided by area of, you can write, cross section. So now see, like this normal to the area of cross section, also in two way force can be applied. So one is by pulling this. In this situation we are creating tension in this material. Another, if I am applying force in this manner, then we are trying to compress it, then compression will be there. So based on that, this type, when this force is being pulled apart, some tension is being created in this. We call this is tensile longitudinal stress. Another case is compressive longitudinal stress. So tensile longitudinal stress. So you can say this example is the case of tensile longitudinal stress. F sigma longitudinal, but it's tensile, that will be equal to F divided by area of cross section. So this result in this create tension in the solid, and it elongate, because that will be the result or effect of this tensile stress. Another is compressive stress longitudinal. In general terms, both, because in both cases the force applied, deforming force or the restoring force, is perpendicular or normal to the area of cross section. So cumulatively, collectively we call both as longitudinal stress. So in this situation here, this is our material solid, right? And now in this situation force is applied in this manner. So what it's trying to compress this, is it? So compression effect is created in the solid. So this here it will be compressive longitudinal stress. Longitudinal because its force is normal to the area of cross section. So this will be your, again formula will be still same, F divided by area, but it create compression in solid. So this is about definition of longitudinal or normal stress. Similarly, there are other ways. Another is called shear stress. Shear stress. Shear stress in this situation, actually just look at it, look for this case. So this is a block and we are applying, so here for your better visualization, let's say it's area, this area I'm taking it A. Now in this situation I am not applying force normal to the surface area, I am applying force along the surface. So in this situation the force is applied along this surface and on bottom surface this way, is it? Now you must be feeling the difference here. Actually it's different from, because for longitudinal force, longitudinal stress, always force is normal to the surface area, but here it's along the surface. So this creates shear effect. Here the deformation is different from the case of longitudinal force or normal force, where either it's tensile or compressive. So that's why here we need to define another term that is called shear stress, and this is termed as like, we denote it by letter tau, and this is shear force divided by area of surface. Shear force, what is that? You can write force applied along the surface. Is it? So this is the surface. Now force is applied along the surface. This force is termed as shear force. That was longitudinal force or normal force, or either tensile or compressive force, because that's creating that type of effect. So here it's creating shear effect. Shear force means when a force is applied along the surface, and this is termed as shear stress. Shear force divided by area of surface area, that is termed as shear stress. There is one more term for this. That is called tangential. Remember the difference between tensile and tangential, because it's tangent actually to the surface. So this is also called tangential stress or tangential force divided by area. That is same. Shear stress or tangential stress, that means exactly same. And the next one is bulk stress. It's little bit different. Now here what is happening, on one face we are applying some force. So on a solid, is it, if force is applied from all side, is it, normal to surface like this, is it, that the deformation will be like something different here. Its complete volume will be getting compressed, is it, or decreasing. So when force is applied all along our surface, right, in this manner, so this result in, like, you can say sort of like bulk stress. It's basically, bulk means more, is it, stress here like this. So that's why that result in this type of stress is termed as bulk stress. So here, now how we calculate, actually first thing is force will be applied from all side, and that too it's normal to its surface. So here we take actually one small element, like here this force F dF divided by its area dA, then this bulk stress sigma bulk is defined as dF divided by dA, and this actually comes out to be, because this type of stress is mostly we deal when we are dealing in terms of some solid object placed inside, let's suppose liquid. So what will be that? That will be like pressure actually is acting. So this is force per unit area that become equal to, this is called pressure actually. So bulk stress is equal to your pressure stress or pressure simply. These are three type of stress. Now these stress definitely once applied on a solid, what will happen actually? Some deformation will be created in the solid, and yes, we define few terms. So let's measure that deformation, let's define the terms related to that, and we call that as strain. Before that, let me solve few cases, few problem on it. Okay, let's see simple application of stress, different types of stress. So find out longitudinal stress and shear stress on a fixed solid block. This is a fixed solid block, and on this surface we are pulling it with 100 Newton force at this angle. So first we need to resolve this into, so this is F cos 30 degree and this is F sin 30 degree. Another point is dimensions of block is given. For stress we need area. So the question is which area we should be using, and that should not be a big issue for you, because on the surface, like forces acting, we should consider the surface area of that surface. So here you can say this is the surface at which force is acting. Another point here, force is like directed or acting at single point according to the diagram, but we will not consider it like that force is acting on just only on that point. We will assume it's uniformly distributed over the complete surface. So that's why like we got, so now we can easily, so the normal force divided by total area will be your longitudinal stress. This is the force along the surface, so that is called as shear force, divided by again same surface area, that will be a shear stress. So we can easily answer it. So longitudinal stress sigma longitudinal will be equal to what? F sine 30 divided by area. F sine 30 100 into sine 30. And what is the area? Area of this is 5 multiplied by 2, 5 into 2, and this comes out to be 100 sine 31 by 2 divided by 10, and this comes out to be 5 Newton meter square. This is longitudinal stress. Similarly, shear stress, that will be shear force tau. Shear force is F cos 30 divided by area will be same, 5 into 2, so this is 100 root 3 by 2 multiplied by 10, and this will be 5 root 3 Newton per meter square. This is longitudinal stress and this is shear stress. Let's see next case. Find out the bulk stress on a spherical ball. This is a spherical ball of radius. Its radius is also given to you, r 10 by pi centimeter. And if area and mass of the piston is 50 centimeter square and 50 kg respectively for a cylinder filled with gas. So from outside pressure will be acting and there will be gas. So because piston is in equilibrium, then I can write P gas is equal to what? P naught plus this mass of piston mg divided by area of piston, that will be pressure inside this, and this is P naught, we can write atmospheric pressure 10 to the power 5 Pascal plus mass is 50 into g 10 divided by area is 50 multiplied by 10 to the power minus 4. So this gets cancelled, that is equal to 2 into 10 to the power 5 Pascal. So this is the pressure of gas. And another thing is, what will be the force acting on this ball normal to its surface at every point? That will be equal to simply pressure. So we can write bulk stress is simply equal to P gas, and that is equal to 2 into 10 to the power 5 Pascal. So this is the answer. So that is simple application calculation of bulk stress, longitudinal stress and shear stress. So I hope by this time you just you should be clear with what is like elasticity, plasticity, definition, why solid shows some like elastic and plastic behavior because of different arrangement of atoms and molecule in their lattice, in their solid, that result in all this behavior. Then we are more on like in this chapter focusing on the properties, that like mechanical properties, stress, strain, different types and somehow related. So let's continue here from here onward in the next class.